Hello and welcome everyone. My name is Nour and I'm from the UK Customer Success Unit. I am here today to talk to you about agent-to-agent communication lab using MCP, built on top of APIM and Azure Container Apps and other components from the Azure stack. So without further ado, let's delve into the architecture and why we are considering agent-to-agent communication. So this is the basic architecture that we all know and we're familiar with when it comes to building MCP-enabled agents, either using AI Foundry, Semantic Kernel, or O2Gen, with the use of Azure API Management as a middleware where it can handle with all policies and controls, can handle some authentication, authorization, and different capabilities, advanced capabilities for managing your back-end remote MCP servers. Your remote MCP servers could be based on or deployed on an Azure Container App. It could be a third party, and you can use pass-through capabilities that are available from APIM. It could be based on a REST API that you're transforming into an MCP on using the APIM MCP serverless capabilities. So many things that we can do in this space. And this is not going to be surprising anyone. Let me show you how that actually looks like when it comes to an implementation. As you navigate into the lab, you will find that it is broken down into two sections. One that is related to deploying all the infrastructure and assets related to the lab and the extension of it, but also the MCP agent-to-agent as MCP servers. Let's delve into it. Let's break it down one bit at a time. So in the previous diagram, which I have showed you here, we're just going to be deploying a simple Azure OpenAI, some MCP tools, and Azure Monitor policies and basic policies, and a basic agent that will be calling the different components that we have behind APIM. So as I go into the lab, I have taken the liberty of running some of these cells in advance to make sure that we don't waste a lot of your time on this video. So what I have done here is I have initialized the lab, initialized the notebook. I have some parameters here, such as where my Azure OpenAI resource is going to be, what is this queue for APIM, where is the resource group is going to be located. For example, here is going to be in West Europe. And I am having certain code that is available here. I will dive in with you in a bit to see how that code is structured. Then I'm verifying that I'm having the right credentials, the right access to my tenant, and then I am running the deployment. Running the deployment is based on a bicep template, which is captured here. It doesn't have any credentials or anything, so it's highly customizable and you can do whatever you will with it, really. What it will do, this bicep template, what it will do is it will implement all the infrastructure that is associated for these two labs. One that is based on agent-to-agent communication using MCP and the other one using the A2A protocol from Google. It will deploy an Azure OpenAI resource. It will deploy a couple of MCP servers, Azure Monitor, API Management, MCP agents, or A2A agents will be deployed on top of Azure Container Apps. So after the deployment has been successful, for this example, this deployment has taken me around 4 minutes to run. As you go through it, you will see some of the parameters that I have extracted. And then I am building my MCP tools, which is again very basic weather MCP server and an on-call MCP server, which is all what they will be doing is they will be generating some random responses as an API in response to some of the calls around either cities or on-call. So what we will be doing next is that we will be testing the policies and we will be testing the implementation that we have at this stage. So if you think of this as a three-tiered architecture, the first layer here is around the platform, all the tools that you will be having. And at this stage, I want to be able to test this entire box together. I want to be able to test that I can access my Azure OpenAI implementation or deployment from behind APIM. I want to make sure that I'm able to access my MCP servers. And I also want to be able to categorically see that my assets has been deployed and is being monitored. So this is a very simple code base that will connect directly to the MCP servers through APIM. So for example, I will be listing the tools that are available to me either to the on-call or the weather MCP servers. So if I execute that, I can see that the weather MCP server that's currently using SSE is having two tools. One that is get cities, the other one is get weather. The on-call is having just get the on-call list, really. The implementation that everyone is familiar with is that I am going to be hooking one agent to my MCP tools and keep growing the number of tools irrespective of what is happening. So here what I'm doing is I'm just simply connecting my weather plugin, I'm connecting my on-call plugin, and I'm going to be using semantic kernel for this, and we'll be passing on the plugins that I have as weather and on-call. And in this case, as you would expect, it will be a single agent that will be able to break down its request across multiple MCP servers. So when I run this, for example, it will need to make several calls to the back end, which are the MCP tools. So for example, here I'm saying, what's the current weather in Lisbon and in London, and who's on call today? It will make some calls back to the MCP, which we will not be showing here, to give me some random details around the weather in Lisbon and the weather in London and who's expected to be on call. So far, so good, and it really doesn't add too much to what we already know and how it already works. Now, why do we want to add multiple layers? Why do we want to add agent-to-agent communication to the mix? This is where things get really interesting. Because, for example, let's say that you're having 100 tools or 100 MCP servers, and each MCP server will expose its own tools, will expose its own way of doing things. Sometimes you might even end up with some functions that sound similar or will have similar annotations. So how the model will be able to react to that, the LLM model. Some models will react better than others, but the rule of thumb is that as the number of tools that are available to an agent or to an LLM increase, the quality of the responses will degrade. So the ideal scenario is that you want to break down your agents into smaller agents that each is capable of handling a set of processes or a set of APIs in order for you to be able to maximize the quality that you're getting from your agent. So this is number one. Number two, you want to be able to potentially sell your agents as a service. So instead of just selling an API endpoint or offering API endpoints either as a microservice or as a third-party product that you want to offer to your customers, you might want to add agentic capability as a service. And this is where, for example, you might want to reduce the scope that is available to a particular agent. And this is why I want to introduce you to this multi-tier agentic architecture. At the bottom layer, we will be looking at the tools. This is where you will be having your Azure OpenAI, your MCP servers, either first-party built by Microsoft or something that you have transformed your API into an MCP server using the serverless capabilities in API management, or a third-party MCP that you're using or you have purchased from a completely different provider. So this is kind of the lowest denomination of the capabilities that you have. The second layer that I want to introduce you to is the agentic layer. This is where you're building your agents to use specific or a subset of your MCP tools. And in this example and this lab that we will be demonstrating, we will be hosting this on Azure Container Apps. Azure Container Apps is a very powerful and a potent tool that you can scale down to 0, but also you can burst up whenever there is a hot path in your code, or there's a high number of volume of requests that are coming in that you want to make sure that you're able to cater for. We will be using semantic kernel as well. And semantic kernel is super powerful because you can create either an agent, you can create your preferred connectors, you can create your own preferred strategy, and then wrap this up into an MCP server. We will explore how this looks like in the code. And then at the top end of the spectrum, this is where the end user would be coming in from. This could be your real-time audio. This could be a third-party application. It could be an orchestration of multiple agents or a process organizing multiple agents. So this is a rehashing, if you will, of the 3-tier architecture that everyone is familiar with around the world, where you will have your services, then your agents, and then your top-level orchestrator. So far, so good. Let's pause for a second. One of the coolest features that have made it recently into semantic kernel is around transforming any code as or any agent as an MCP server. So let me show you an example. So for example, here I have created a function, and this function is just building an agent. And here I'm saying I'm having an agent that is a chat completion agent built using semantic kernel with Azure Chat Completion as a service. And it's as simple as just pass it on with some MCP plugin. Now that we have created our agent and returned that agent from the function, we will be wrapping this up into an MCP server. And this is something that is very powerful in the semantic kernel SDK, and it's available both in C# and in Python. The demo here that we're seeing is obviously in Python, just for simplicity and demonstration purposes. One of the things that I'm doing here is I am adding a prompt template. And this prompt template will give me an example of what a good prompt that I could send to my agent in order to be able to respond effectively. And here, for example, I'm going to be adding this. This creates a prompt for a full list of report of the location given. And the last thing I'm going to be saying, kernel as MCP. As simple as that. I am just going to be exposing my kernel as an MCP server, and this is going to be its name, and this is the prompt or prompts array that I'm going to be making available. So if I go back into the architecture here, what I have just done is I made this exposed potentially as an MCP server in order for it to be hosted on Azure Container Apps. And then I'm also having additional parameters where you can have multiple transports, so HTTP, SSE, and STDIO, and just a simple wrapper around it, really, to get you to choose which transport to use. Which means that irrespective of where your agent is going to be hosted, either locally or remotely, or using streamable HTTP or SSE, you will be golden to run it without any changes to the agent that you have, which means I can go back here, and instead of having a chat completion agent, this could actually be a team of agents running within semantic kernel. Going back again into the MCP as agent-to-agent communication. Now, this is the second part of the lab. The first one, as we have described, was just deploying the infrastructure, was just making sure that everything worked up to this point. Now we want to build the next layer. The next layer here, where I will be hosting my semantic kernel MCP servers and exposing those through APIM, and then using them through another agent. So here, as I'm running the second part of the lab, I'm just reiterating on the reinitialization of the lab. I am retrieving the parameters for my deployment, which have already been done. And then I have taken the liberty of running these builds so that it will build a server image, MCP semantic server, semantic kernel server image, and deploying them on my A2A agents. And then the next step here is I am exposing two things. One, just for testing purposes, and I'm going to show you how that actually works in reality, but also through APIM in order for us to be able to fulfill this multi-tiered architecture that we're describing here. Now, this is where the magic happens. This is where I'm having an O2Gen agent of multiple MCP agents. So here I am going to be providing the link for my weather agent and then making sure that I'm connecting to it. I'll also be connecting to my on-call agent, connecting to it, and then I'm going to be creating an assistant agent, an O2Gen assistant agent, and I'm going to be passing it weather agent and the on-call. And I am going to be executing it using the same prompt of what is the weather in Lisbon, Cairo, and London, and who's on call in CAT today. Remember when we did run this previously, we had a look and it was a single agent and it's just communicating with the plugins, i.e. the tools. And obviously we know that in the backend, it will be calling the functions and will be sending the parameters directly to the function and retrieving the response. Here, however, when we execute this, let me execute it again, we will see that it is doing something slightly different. Yes, it is treating each backend MCP agent as a function, but now it's passing a human readable question. What's the weather in Lisbon? 1. What's the weather in Cairo? What's the weather in London? And another one, who's on call in CAT? And each is going to a different agent, as we can see here. And according to that, we're getting also 4 responses. One from about the weather in Lisbon, another one about Cairo, another one about London, and then the agent will aggregate all the responses in one go, as in the agent of agents, weather in Lisbon, Cairo, London, and who is on call today. This is the power of agent-to-agent communication. You can now have service level security, you can have agent level security, you can have even authentication and authorization per call for everything that you're doing throughout your agents, and making sure that the scope for all of your agents is locked down and is being tracked. This is the same implementation, but this time using semantic kernel, agent of agents. And here I am asking it exactly the same question, Lisbon and London, and who's on call today. It done its own backend calls and came back with the responses. In order to see these queries in the background, I am going to be going to my implementation, which is the resources that I have. For example, I will look into the ACA weather agent real-time logs, and you will be able to see that the message that has been received, the current weather in London and in Lisbon, and it is calling other back-end services. So to go back again and to wrap things up, this multi-agent architecture will allow you to create a lot of servers, a lot of MCP servers as agents, which are in turn are able to wrap up more complex logic, more instructions, and more prompt engineering. So you're able to segregate what you can see and separate your front-end agent from your middle tier agent from the back-end tools. This becomes very helpful in order to make sure that you have a scalable implementation that can adhere to zero trust architecture, but also allows you to scale up and down as you please. Something that is very noteworthy, the code that is demoed here is not production ready. It needs a lot of server lifecycle, retry, and recreating the connections over and over again, because obviously as the internet has it, connections will die. If you have a long-lived HTTP connection, it will eventually die, it will eventually crash. So please make sure that if you decide to adopt this code as a base for your multi-agent architecture, that you implement these fail-safes, these retries, the retry mechanisms, and so on and so forth, to make sure that it is trustworthy for your production environment. I hope you found this useful, and please keep your feedback coming. It's really helpful and will help us make more better sessions in the future. Thank you very much and have a great day.